In this section, we are going to look at angle measure. And to do that, we first need to start by looking at what we mean by an angle. An angle consists of two rays with a common vertex. And so here we can see that ray 1 and ray 2 share a vertex, and theta is our angle between the two rays. We often begin an angle with a ray, and so we'll call this ray 1, which we'll think of as our initial ray, and end the angle with ray 2, which we'll call our terminal ray. If the rotation is counterclockwise, much like with the unit circle, then the angle is positive. If the rotation is clockwise, then the angle is negative. So as I've drawn this ray here, ray 1 going to ray 2, this would be a positive angle. And again, depending on where we start and stop. And just like with our unit circle, we'll usually start our rays with our initial ray being at the x-axis where theta is equal to 0, and then move either in the positive or negative direction. There are two types of measure for any angle. There is radian measure and then there's degree measure. Recall, if a circle of radius 1 is given with a vertex of an angle at the center, then the measure of the angle in radians is the length of the arc that subtends the angle. Again, all that means is that if we're looking at the unit circle, and I take my initial ray out to some terminal ray, that angle is going to be centered with the vertex at the origin, and we consider the length of the arc the measure in radians. So again, if I had my terminal side at the y-axis where my value is 1 on the unit circle, I would just be looking at an angle length of pi over 2. So to find the angle in degrees, we have three relationships that you're going to need to know between degrees and radians. The first one is that for every pi radians, we're looking at 180 degrees. And so again, if you're thinking of the unit circle, that means half a revolution is equal to pi radians, or 180 degrees. A full revolution of the circle is going to be 360 degrees, or 2 pi radians. So to convert between the two, 1 radian is going to equal 180 over pi degrees, and 1 degree is going to equal pi over 180 radians. Okay, and we'll use those two things, those relationships mainly, to convert between radian measure and degree measure. Okay, so for example, let's convert the following radian measures to degrees. Let's say theta is equal to 7 pi over 6, and we want to convert this to degrees. Well, the first thing we're going to do is we're going to, because it's in radian measure, I'm going to multiply by the 180 over pi in order to get it into degrees. And so here we can see we get that theta is going to be 210 degrees. If theta equals 3 radians, I can do the same thing. I'm going to multiply by 180 over pi degrees to convert my angle to degree measure. So in this case, theta is going to equal 540 over pi degrees. Now, one of the things to notice is obviously in both these cases we're using the same conversion, but they don't always come out to be nice numbers. That's okay. When you're doing your assignments, whether it's the ALEKS or the written work, only give the decimal approximations if you are asked for them. Okay. So now let's look in the other direction. We want to convert a degree measure to radians. So here let's look at theta equaling 72 degrees, and we want to convert this to radians. So here we're going to use the conversion to radians, which is the pi over 180, and turn it back into, to turn those degrees into the radians. So here the 72 times the pi over 180 will give us 2 pi over 5. Here you don't have to write the RAD for radians. Any angle that doesn't have the degree symbol, you should automatically assume that it is in radians. Okay. So let's look at another one. Let's look at theta equaling negative 45 degrees. So again, to convert to the radians, we'll again multiply by pi over 180 and then simplify. So here, when we do the calculation, we see that theta equals negative pi over 4. So recall from previous sections coterminal angles. So remember, coterminal angles are any two angles that are in standard position that have the same initial side and the same terminal side. Usually the difference between them is the number of revolutions or partial revolutions that you'd have on the unit circle. Okay, so again, just like we did before, we want to be able to find two positive and two negative angles coterminal with the given angle. The only difference here is we're not only looking at radian measure, we're also going to do some degree measure. So for this first one, let's look at 135 degrees. We want to find two positive and two negative coterminal angles. So for the first positive, again, I'll find my angle, so at 135, and then I just want to add one full revolution. So in this case, because we're looking at degree measure, we're going to use 360 degrees to determine our full revolution. So our first positive coterminal angle is going to be 135 plus the 360, or 495 degrees. Now we're going to do the same thing to get the second positive coterminal angle. So we're going to take 135 plus 2 full revolutions, so 2 times 360, to get 855 degrees. Okay, so there's our two positive. Now we're going to do our two negative. So to do the two negative, we're just going to subtract a full revolution. So here we can see 135 minus 1 revolution, or 360 degrees, is going to give us negative 225 degrees. Okay, to get the second negative coterminal angle, we're going to use 2 full revolutions. And so here we can see that using 2 full revolutions, we get 135 minus 2 times 360 is going to equal negative 585 degrees. Now with the radian measure, again, this is very similar to what we did before. So to get my first coterminal angle that is positive with 11 pi over 6, again, I'm going to add a full revolution, or 2 pi radians. So we're going to get 23 pi over 6 for our first positive coterminal angle. For the first negative coterminal angle, again, we're just going to subtract 1 revolution. And so subtracting 2 pi, we see that we get a negative pi over 6. I'll leave you to check the second positive and second negative coterminal angles. An angle whose radian measure is theta and is subtended by an arc of a circle with radius r will have an arc length of s, where s is equal to r theta. So given any angle in its standard position, we can find our arc length, or the value of the distance around the outside of the circle, by finding our radius and the angle in radians and multiplying those two together. Okay. So for example, let's find the length of an arc that subtends a central angle of 2 radians in a circle of a radius 4 miles. So there's our picture. We've got a circle with a radius of 4 miles and an angle of 2 radians, and we want to find the arc length. Now in this case, because our angle is already in radians, we can just multiply the angle by the radius. So our arc length is going to be 8 miles. And again, notice that the units on our arc length are the same as the units on our radius. Let's look at another one. A circular arc of 3 feet subtends a central angle of 25 degrees. We want to find the radius of the circle. Now in this case, we're using the same formula, but now we're solving for r instead of s. And notice here that our theta is given in degrees. Okay, so the first thing we're going to want to do is start by converting our theta to radians. So again, to do this, we're going to start by multiplying our 25 degrees by pi over 180, and then simplifying to get 5 pi over 36 radians. So now we can put this information into our arc length formula to solve for r. So plugging in 3 for s and 5 pi for 36, we'll go ahead, 5 pi over 36 for theta, we'll divide out by the theta to get 108 over 5 pi. And again, for most of our problems, if we're looking for an exact solution, that would be our r. Again, don't forget your units, which is in feet. Or if we are asked to simplify this to a decimal rounded off, we would say that r is approximately 6.88 feet. So given the arc length, we can define a sector of a circle to be the pi slice cut from the circle with an angle theta and arc length s. The area of the sector is given by 1/2 r squared theta, where theta again is given in radians. So our picture would look like the following. Given a circle with radius r and arc length s for the central angle theta, the green slice there would be our sector. Okay, and the area of that sector would be the 1/2 r squared theta. So in an example, let's find the area of a sector with central angle 1 radian in a circle of radius 10 meters. So here again, we're going to start by looking at our formula and plugging in the information we know. So we know that r equals 10 meters, theta equals 1 radian, and the area is 1/2 r squared theta. So plugging in, a sector of a circle has a central angle of 60 degrees. Find the area of the sector if the radius is 3 centimeters. So here again, we want to find the information that we know and then plug it into our formula. So we start with, we know the radius is 3 centimeters and the central angle is 60 degrees. But notice again for our formula, our theta has to be in radians. So here we need to convert our 60 degrees to radians. So theta will equal pi over 3 radians, and now we can plug into our equation. So our area will equal 3 pi over 2 centimeters squared. The last concept in this section is circular motion. So let P be a point that moves along a circle of radius r, and as the point moves, it creates an angle theta at time t. S is the distance the point travels in time t. The speed of the object is then given by two different formulas. We have what we call the linear speed, which we can think of as if we were walking around the outside of the circle, the speed at which we would walk. So v, or for velocity, is equal to s over t. Okay, so the distance over the time. And then there's the angular speed, which we can think of as the rate that the angle is changing with respect to time. And so we'll call this omega, which looks kind of like a W. Omega will equal theta over t. There's a nice relationship between our linear speed and our angular speed, and that is that the linear speed is equal to the radius times the angular speed, where v is equal to r times omega. These formulas in the box are two that you should be fairly familiar with. In this class, we'll do some things with it, and you may be asked to use these. Definitely for later classes, you should know how to find these. So I would suggest memorizing these formulas or really understanding how to get those formulas at this point. So let's look at an example that uses both linear and angular speed. So a ceiling fan with 16-inch blades rotates at 45 revolutions per minute. That's the RPM. We want to find the angular speed of the fan in radians per minute. Okay. So again, the angular speed is looking at the rate that our angle is changing with respect to time. So as our blades move around, if we picked one of the blades and looked at it from the initial angle 0 through some positive angle, we want to figure out how long it takes to get to that particular point. Okay. So remembering our formula, it's going to be theta over t that is going to equal our omega. Now these formulas are what we'd consider cancellation type formulas, we're given a value in certain units, and we're going to set up the equation to cancel out the units to get what we want. Since omega is in terms of theta over t, that means our answer for theta, for omega, should be in the units of theta, which in this case is radians, divided by the units of t, which is our time, so in this case minutes. So we'll start with our RPM. We know 45 RPM is 45 revolutions in 1 minute. Now the revolutions, we want to convert this to an angle. So remember that each revolution of the unit circle is 2 pi radians. And so we can say there are 2 pi radians in every revolution. So now we have, if we cancel out our units there, we can see the revolutions cancel out and we're left with a radians per minute. So here we can see that omega is going to equal 90 pi radians per minute. For part B, we want to find the linear speed of the tips of the blades in inches per minute. Now here, the reason we look at the tips is because, again, for linear speed, we're thinking about walking around the outside of the circle. So I'm not really caring so much what happens in the middle now. I want to know what happens to that point right around the edge of the circle. And so that's why we're saying the tips of the blades. Now here, again, our speed we want in inches per minute. So again, I'm going to start with that 45 revolutions per minute and then convert it to the units that I want. In this case, for a linear speed, I need it in a distance, which is our s, over our time. So again, we'll start with the 45 revolutions per minute. And here, we're going to look at the number of revolutions per radian. And now if we think about the distance that's traveled, so remember that these are in terms of, we can think of this in terms of arc length. So as the theta moves, our distance is going to change. So for each radian, we're looking at the unit of how far the blade is going to be from the center of the angle. And so here we can think of that as the 16 inches. That's our radius. So now we can put this all together and find our linear speed. So our linear speed is going to be 1,440 pi inches per minute.